Hello wonderful person, this is Anton, and in this video we're going to be discussing a milestone in physics that's technically 50 years in the making. Because for the first time in history, scientists have successfully built a clock powered not by electrons around the atom like in a typical atomic clock, but instead by the very heart of the atom, its nucleus. Or basically, in 2026, we've now officially entered the nuclear clock era that researchers have been trying to achieve for the past few decades. And so in this video, we're going to discuss two separate studies from June 2026, based on two independent teams, one based at the Vienna Center for Quantum Science and Technology in Austria, and another one led by the Tsinghua University in China, with both teams producing the results that suggest that we're now not just theorizing about this, but they've now successfully built a nuclear clock able to keep time with so much more precision than ever before. And so in this video, let's discuss exactly what this means, how some of this works, and of course discuss the implications for modern technology. But I guess first, the more obvious question: why do we even need a new clock? Because you might be wondering, Anton, we already have so many accurate clocks, or basically these atomic clocks, accurate to approximately 19 decimal points. Or essentially, they seem to lose 1 second every few million years. As a matter of fact, some of the more advanced atomic clocks, those based on ytterbium and strontium atoms, seem to be even more stable, losing just 1 second over the entire age of the universe, or approximately 14 billion years. But the problem is that all of these clocks have a kind of a fundamental limit. They essentially rely on electrons, and specifically electrons orbiting the nucleus. And because in this case electrons are on the outside of the atom, despite their relative precision, they're still surprisingly sensitive to their overall environment. For example, various electric fields or stray magnetic fields, or in some cases even just pure heat, can actually nudge these electrons just enough to induce a slight change in the ticking and basically produce occasional errors. And so in that sense, when it comes to the atomic clocks, despite their precision, they still do have a tendency for occasional errors, and most importantly, they're just very expensive to maintain. And in that sense, a nuclear clock changes the game entirely. And that's because, well, nucleus is 100,000 times smaller than the atom itself, and is also deeply shielded by those same electrons from the environment outside, and so the nucleus is almost immune to outside interference. And because most nuclei possess some kind of a natural resonance, not a lot of things can disturb this resonance, making nuclear clocks just naturally more accurate. As a matter of fact, at least 10 times more accurate compared to the best atomic clocks based on the electrons that we have today. And well, theoretically, scientists have known this for a very long time, but the problem was, of course, trying to create this and trying to make it work. And that's because fundamentally, scientists are measuring something slightly different. Inside a typical atomic clock, the main measurements is the electron transition from one energy state to the other. But in the nuclear clock, here the energy transition happens inside the nucleus and are generally hidden from the outside world and somewhat difficult to measure. And so the strength of the nuclear clock is also its kind of weakness, I guess. It's insensitive to interference and is not affected by the external electric or magnetic fields, but as a result is also kind of difficult to measure because it's difficult to detect what it's actually doing. But nevertheless, this still represents the next frontier in precision timekeeping, just because here nuclear clocks would be fundamentally much easier to maintain and thus very likely much cheaper. But there was a major milestone, or I guess a major discovery, back in the 1970s. And this was a discovery from the Idaho National Engineering Laboratory, whose researchers discovered the isotope that seems to make things so much easier. Here they discovered a unique quirk inside an atom of thorium-229. It seems to contain a very specific transition that's potentially accessible and measurable using laser technology. In other words, unlike other atoms where this would be extremely challenging to detect, inside this one specific atom of thorium-229, and specifically inside its excited nuclear state, the energy level seems to be close enough to its ground state that some of the high-precision lasers should be able to detect it and manipulate it. But it wasn't until 2003 that we finally had some of the first theoretical propositions. And so in this case, Eckhard Paik and Christian Tam from Germany formally proposed that using specific nuclear transitions can be used for time measurements using these specific atoms, which was the official beginning of this race to build the nuclear clock. And by the way, this was like 23 years ago from when I'm making this video. But it wasn't until over a decade later, in 2019, that two independent international teams successfully measured the exact energy inside Thorium-229. This was achieved by the team whose paper you can find in the description. And this was a relatively big deal. It basically provided the precise data required to target the transition inside these atoms using lasers. But it took approximately 5 years to make this physically happen, when in 2024, multiple teams from Germany, China, and America successfully excited the atoms using very specific vacuum ultraviolet lasers, officially proving that we can physically control these atoms and force them to transition into different states by using modern lasers, and actually relatively accessible lasers, making all of this relatively cheap. And this is also one of the most important achievements here, because normally, in many different atoms, in order to shift them from one state to the other state, we actually require ridiculous amounts of energy, and very often something involving X-rays or even gamma rays. And so decades ago, we didn't even have lasers capable of doing any of this. But this Goldilocks isotope of Thorium-229 turned out to be just this unusual anomaly that can be manipulated with ultraviolet lasers. As a matter of fact, as of 2026, this is the only known nuclear transition, and here we're talking about all of the elements known to us that the current laser technology can actually directly interact with and affect. This would be practically impossible with any other atom or any other isotope. With some of the more recent achievements in 2025 and early 2026 now showing that we can also do all of this by just using thorium atoms on simple metal surfaces like stainless steel. Basically, dramatically simplifying the construction and dramatically lowering the cost of this clock, not to mention also making it much safer. And well, that's one of the main achievements from one of these recent studies. Both the European and the Chinese teams build these clocks on a kind of a solid-state approach. And so instead of trapping single ions in vacuum, which is how most of the atomic clocks usually work, here they embedded billions of Thorium-229 nuclei inside a calcium fluoride crystal. And the general principle in this case is pretty simple. First, you have the oscillator, and that's something that's required for any kind of a clock. We need something that repeats. And well, in a grandfather clock, it's the pendulum. But in this clock, it's the back and forth shift of the thorium nucleus between its ground state and its excited state. Basically, think of it as the nucleus of the atom vibrating between two separate states. Then we need the laser. Here they use the specialized ultraviolet lasers with a wavelength of 148 nanometers. And finally, we need the feedback loop. That's actually one of the most important parts of this 2026 discovery. Because in this case, a clock isn't just a laser hitting a crystal, but instead it's a system where the nucleus essentially tells the laser what frequency to stay at. And so if the laser starts to drift slightly, the nuclei start to absorb less light, and a detector senses this change and then sends a signal to adjust the laser back to its perfect frequency. And so in this case, that's actually what makes this an actual clock. Here this allows scientists to directly measure the frequency of these vibrations, because the vibrating atoms directly provide feedback to the laser, which can then be measured by scientists. And so the team from Vienna demonstrated this operation with the nucleus of thorium successfully steering the laser itself. Whereas the Chinese team focused on reproducibility, showing that two separate crystals, grown in two different ways, still produced nearly identical frequencies. And by itself, this is huge, because what all of this means is that we can eventually manufacture all of this using relatively cheap parts and using a kind of a standardized reference. In other words, that's why this is the beginning of nuclear clock age, because both of these studies now show us that everything here seems to work as intended and everything seems to be perfectly reproducible. And because these clocks are so stable and because they basically rely on a slightly different physical phenomenon, it would make them the most accurate clocks ever created. And clocks that would not actually care about much interference, because nuclear resonance in this case seems to be fundamental and is not affected by a lot of things. But in theory, they could also create some of the most sensitive sensors on the planet, because once again here, even a simple disturbance would be visible because the lasers would be shifted just a little bit. And so intriguingly, just to test this, in the very first run, the Austrian team decided to see if they can use this to maybe search for the ultralight dark matter particles. Now, obviously they're still hypothetical and have never been discovered, but they wanted to give it a try anyway. And that's because some theories suggest that dark matter could be made out of these extremely low in mass particles that could possibly be detected if they nudge one of these nuclei just a little bit. And because thorium-229 transition is actually in a kind of a delicate balance between electromagnetic and nuclear forces, in theory it's about 10,000 times more sensitive compared to atomic clocks when it comes to these particle-based fluctuations. But as you can imagine, so far they haven't found dark matter yet. But they still set a new limit for what can be done and for how sensitive some of these new sensors could one day become, because this can naturally be used for a lot of other things, even detecting things like neutrinos. But despite these achievements, we also have to be somewhat realistic with what exactly we have right now. Because despite the success, this first prototype still does not outperform the best atomic clocks in terms of accuracy. Now, that's because obviously the atomic clocks had a kind of a 70-year head start, whereas these clocks were just created. But this is definitely not something we're going to be using anytime soon. It will probably take at least a few years for all of this to become functional and usable in a lab. But because of this, there are probably going to be some major changes when it comes to science. The first obvious one is going to be the redefinition of what a second is. And so right now, 1 second is defined by the frequency of electron fluctuations inside the atom of cesium. And specifically cesium-133 atoms are believed to transition from their ground state to their excited state 9,192,633,770 times. And so by counting that number of transitions, we're essentially getting 1 second. But once again, this is based on the electron transition, not something that happens inside nucleus. And so a nuclear clock could offer us a much more stable and much more accurate definition involving these thorium-229 nuclear vibrations. At the same time, based on the Einsteinian principles, we know that time moves just a little bit slower, closer to massive objects. And so these clocks are actually precise enough that in theory they can now detect heights of just a few millimeters through the measurement of the changes in these vibrations inside the nucleus. And this can help us map the Earth's gravity and create new gravity maps with a lot more precision, while at the same time potentially helping geologists discover some new hidden things inside Earth that were previously invisible. And last but not least, for theoretical physics, this might help us test a few constants that are still not well understood. For example, the constant governing electromagnetism, referred to as the fine structure constant, could be measured more accurately and even checked if it's a real constant or if it's slowly changing over time, as some of the more controversial studies try to propose. In other words, by having these ridiculously accurate clocks, this will open up a lot of new doors for all sorts of physical experiments and all sorts of discoveries, which by the way is exactly what happened when the atomic clocks became real. And so in conclusion, we've now officially moved from the theoretical nuclear clock to a physical one that seems to be now a working technology. A major step for physics and for science in general. But on that note, once we discover something else, or once an even more accurate clock is produced, we'll come back and discuss this more in some of the future videos. Until then, thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.